Okay, good morning everybody. I hope everyone's having a wonderful day. So before we get started, just as a quick reminder, your final exam is on December 11th, so that's a Saturday. I believe it starts at 2, and it's a 3-hour exam. So just remember, you have to make yourself available for this exam. When it comes to that, the exam, please read the exam format. I put a lot of detail in there. I also must stress that I will have my office hours for the remainder of this week, and I'm not sure exactly how it will be for next week, but I'm planning to, regardless, to probably have my office hours. But if not, we can do it by appointment basis during my office hours, or we'll see. I will let everybody know what my office hours will look like next week. But this week, I most certainly will still have my office hours, even though we don't have class, okay? So you're welcome to drop on by if you have any questions or concerns. And also for timeline purposes, you should be expecting your final assignment mark back by the 13th. So there will be time for that. That kind of question, ask me afterwards for those specific details about the exam. There's one thing I do want to point out to you is that when I post the lecture notes after class today, there's going to be a small reading that I'm going to provide for you that gives you an introduction to parallel algorithms. I'm going to ask you a really basic question about it in the true and false section. But please read that. So it will be in the lecture notes. It'll be one of the very last sections. So I'll point it out to you and I'll let you know by email or message on your courses when that's available. So it'll be available as soon as I post the lecture notes for today, okay? So it's just meant to give you a high-level view of what parallel algorithms is about, and I'm hoping that it'll entice you to look into it a little further. So that being said, I want to pick up to where I was last day. So hopefully everybody's having a wonderful Monday, because I know I am. I'm really excited. It almost feels like we just started the course. In some sense, it feels sort of like that symbolically with this topic that I'm getting into. So last day I showed you what we had as a polynomial time reduction. So remember, in this concept, the idea is that if I give you some instance to some decision problem, remember decision problems, they have yes instances and no instances. And the idea is that I want to use this polynomial time algorithm, which we call a reduction, to transform or construct an instance of the problem I'm interested in so that I can show that there's a direct relationship between the two. So for example, if I wanted to show that there exists a polynomial time reduction from the Hamiltonian cycle problem to the decision version of the traveling salesman problem, what I can do is perform the following construction. So remember last day I showed you this, is that you use the same set of vertices as in G. And what you do is you just simply, everywhere where you had an edge in the original graph, you put that edge into H. This is the newly constructed graph, where its edge weights are 1, if it was originally there. Otherwise, I introduce a new edge that has weight 2. So those are the green edges on the board. So notice that those are not in G, but they serve a very important purpose. Because remember when I defined the instances for the traveling salesman problem, you remember I told you it's a complete graph. So notice that by doing this, I've ensured that it's a complete graph. The very neat property that I pointed out to you is that there is a Hamiltonian cycle in H, in G, I was getting ahead of myself. In G, so I'm getting really excited about this. So if there's a Hamiltonian cycle in G, then there has to be a TSP tour of length at most n in H. Likewise, if there is no Hamiltonian cycle in G, then there is no TSP tour of length at most n in H. So that's the if and only if, but that's what you get, logically speaking. Now, what does that mean? So if I tell you that, if I give you a yes instance of Hamiltonian cycle, that means that if I use this polynomial time reduction, what I end up with here is going to be a yes instance to the decision version of TSP. Am I given a no instance over here, then I'm going to end up with a no instance over here. And the whole idea is that if I gave you, say, some algorithm for the traveling salesman problem, then I have given you effectively a recipe to solve the Hamiltonian cycle problem. Does everybody see that? So I can give you any one instance of Hamiltonian cycle, and I can use this polynomial time reduction to build me an instance of the decision version of traveling salesman. And then I just run my algorithm for the traveling salesman problem, and I can tell you if the answer is yes, then it most certainly will be the answer is yes over there. And if the answer is no, then most certainly the answer is no over there. In fact, if you were to look at my proof that's in the notes, it tells you exactly what the Hamiltonian cycle should look like. That's very often how these reductions work. So has everybody got the general idea of what a polynomial time reduction is? So the whole idea is that this, yes, yes. Okay, so remember the way I defined the TSP instances? It's at most n. However, I must stress that if you actually go and dig into the proof, the construction you get exactly out of G will always produce ones with the length is exactly n. So if you're not satisfied with that, you can always axe this part completely. In fact, you can get rid of it entirely. The point here is that whenever I have a yes answer over here, if you actually look at how this construction works, it exactly builds one where the length is exactly equal to n. But if you look at this instance, because remember, the thing that often, this is not obviously specifically to your question, but it's more of a broader one, is that whenever I prove these things, notice that H isn't an arbitrary graph, it's any graph that I get out as a result of this reduction from G. So notice that this isn't just some arbitrary instance of the decision version of traveling salesman problem. It is just simply the construction of G over there, right? So you know always H will look a very specific way from G. So in fact, if you actually go into the proof, you'll see exactly what you'd suggested, is that it will actually be that the length of, if it's a yes instance, its length will be exactly equal to n, which in this case, at most n will definitely cover that. Most certainly. Now, it's a wonderful question. So yeah, very often a lot of these reductions, remember, the whole idea here is that I give you this and I construct this instance. It's not that I'm giving you any arbitrary instance of my TSP tour. Sorry, my TSP instance. It's that it looks very specific. It's based on G. So when I say if and only if, I'm talking specifically about this H that I get from G. But yeah, it's oftentimes, that's why I said last day, very often when we try to build these reductions, we want the instances to look a very specific way so that we can prove properties about them. So sometimes you may have those obvious thing that's sitting out in front of you, but if you can't prove anything about the relationship between the two, it may as well be useless. Sometimes there are different kinds of reductions for the same thing. For example, I could always reassign the weights to this graph, and I can end up with a different reduction for the decision version of TSP. In fact, there's some ways you can use some of these little tricks to prove all sorts of interesting things. For example, there's a construction that's very similar to this one that shows that if I were to give you any arbitrary algorithm that, say for example, I relaxed it from saying, yes, it has to always give me an optimal TSP tour. Instead, it wants me to give you any one that's kind of arbitrarily close to the optimum, and there's some certainty that it always will do so. You can actually use a reduction very similar to this one to show that no such algorithm exists, unless a certain condition I'm going to tell you about later holds. Meaning that TSP is actually a really tough problem. That's why a lot of people are very interested in it. And it's used all the time in industry. So, has everybody got the general gist of our polynomial time reduction? Because I want to move on to kind of bring this together and marry it with some complexity theory. Because I've given you the machinery, but I haven't given you exactly what we're going to use that machinery for to kind of talk about intractability, trying to give us a basic theory about intractability. So give me 2 thumbs up if we're good to go. Excellent, excellent. So let's head on over here. I'm going to first define a one complexity class for you. So very often computer scientists, especially those interested in algorithms, they really like to categorize problems into these so-called complexity classes. So we would like to know which problems have algorithms that means that they're easier to solve or harder to solve based on our formal definitions of them. So one that's very fundamental for decision problems is this complexity class I'm going to call P. So this is the set of all decision problems that are solvable in polynomial time. Now I've made a note there to say deterministic. For our purposes in this course, we will not really need to talk specifically what that means, but just be aware on a technical level, the kinds of algorithms we've been talking about all are deterministic. If you're interested in the distinction, I'll talk more about that a little later. So that means that so if I look at means for each one of these decision problems, there has to exist some algorithm that can decide those yes and no answers in time big O of n to the k for some k greater or equal to 0. So, and if your problem fits this description, it's in P. So note that I've defined it in terms of decision problems, but we've actually studied many problems that you can see are actually in P. For example, earlier I showed you, well, last lecture I talked about how we can talk about decision problems in relation to optimization problems. And I told you that, oh yeah, there's a decision version of the minimum spanning tree problem, or we want to compute a spanning tree whose total cost is at most some integer k. And we ask, okay, is there one or is there one? Well, you can use Prim's algorithm, like I gave you earlier in this course, to decide this, right? All you do is you run Prims, and you can ask if the total cost of the tree is at most k or not. If it is at most k, then you say yes. Otherwise, you say no, right? So we have many problems that you can cast just like this. And many of the problems we've studied or problems you've seen in your previous courses fall into this class. So usually this is a nice intuitive idea for what we often will call easy problems. But I don't want to say that necessarily, because sometimes there's actually really tough problems that sit in P, but they're not tough in the sense that I'm going to talk about here. So when I mean that's in P, it just runs in polynomial time. What if that polynomial has a very high degree? There's problems like that sit in P. Like, for example, testing if a number is prime or not. If you want a deterministic algorithm for that, usually the best known algorithms for that take something like n to the 5, n to the 6th. If you're given an integer n. No, it's the encoding n, sorry. The encoding of n. So if you give the input size with respect to that, the running time will be something like log n raised to the 6th. It's kind of, it's interesting. There's other ones like this. For example, computing a maximum matching in an arbitrary graph. Some of the algorithms for those tend to take cubic or quartic time. There's other strange problems that you may have heard of, such as linear programming. Those ones actually have polynomial time algorithms as well, so you can cast those as decision problems. Sometimes people call these separation problems. But the point is that there are problems that are indeed very interesting ones that sit in this class. Just some people would call them interesting problems, but they're most certainly solvable in polynomial time. But this intuition of tractable is really what I want to talk about. So whenever something like our algorithms run in polynomial time, based on that definition, I'll usually refer to this as tractable. It's not the perfect definition, but for the problems we're going to be interested in, it's perfectly fine. There's a clear separation that's going to happen between these types of classes, at least at this granularity. So, however, there's other problems that don't really fit into P, really. I've talked actually about some of these already. For example, we talked about 0 on knapsack, and I gave you a dynamic programming algorithm for 0 on knapsack. Do you remember the running time for that then? It was pseudo-polynomial, but if you actually break it out, it actually runs in exponential time. But what do we do with those? So for example, TSP decision there, one of its best known algorithms is a dynamic programming algorithm. It's called held carp. it uses very much the same principles as what you see with the 0-1 knapsack, except there's some technicalities involving how you select subsets of vertices with that one. So we talked about knapsack, but we didn't really talk about the decision version. You can always cast this as a decision problem where instead you ask, if you give you the items with their weights and profits, is there a knapsack whose total weight is at most W, but its profit is at least some integer K? So if you ask that, that's a decision problem, but we don't know how to solve that in polynomial time. And also Hamiltonian cycle, that we also don't have polynomial time algorithms for deciding. So we would like something to characterize these, because it's really not clear, like, okay, so I want some way to talk about those. So here's an interesting idea, and this is actually an intuition that comes from a course like CS 411, if you're interested in that course. So what we want to know about is, say if I don't know how to find efficient algorithms for them, can I at least check if if I give you some potential solution, is there some way to verify that it is in fact a yes answer? So if I give you some yes answer, is there some efficient way I can verify somebody gave you one of these solutions? Is there even a way efficiently to do that? Another way you can talk about this is there a short? So short, this is going to mean that it's going to be polynomial in the length, polynomial in the input size. So it's a short, easy to check. So easy to check meaning that there is a polynomial time algorithm for checking the following. Proof, so somebody presented you some solution. So imagine this is that's what I'm referring to as a proof, is they can give you some description of some solution, and I want to be able to check it. So if I check it against the instance and I say, hey, look, yeah, this is indeed a solution. I want some efficient way to do this. Some people like to call this a certificate. And if I wanted a test, I like to think of it like a test. Imagine I have some test to verify if that's a yes answer. So I want to just, before I get too ahead of myself, I want to give you a quick analogy just to explain what I mean by this. Because this sounds a little strange at first, because up to this point, we've always been interested in, okay, I have a problem, I want to find a solution for it, right? So now instead, I'm going to be interested in the question of, okay, so if I give you some problem, if I give you some proof, so remember, I must stress that there is some proof. There's going to be a short, easy to check proof. As long as this exists, I want to be able to if you give me one of these proofs or certificates, I should be able to tell you that yes, this is indeed going to be the case. So if I check it against the instance and I tell you, yes, this is in fact an answer, or no, this is absolute nonsense, and that isn't a yes answer. It should be able to tell me this. And the analogy is really quite simple. At first, it sounds really alien and strange, and this is often something that students tend to have a difficulty grasping, and that's okay. I know I was there once, at one time when I was learning this stuff, and it happens to almost everybody. And I lost my turtle. The turtle was a little spooked. So let's... So I want to define a couple of quick things. Now, I must stress that if you're really a technical aficionado that really wants to get into the nitty-gritties of these things, I did include a formal definition of what I'm going to describe here, but for the purposes of time, I'm just going to keep it high level because that's going to be really what you're going to be responsible for at most. It's just a high-level view of this. So in plain language, for any yes instance, given a proof, I'll put in quotation marks, given a proof that is short, is there a polynomial? The puppies are quite excited about this. Is there a polynomial time algorithm? And I'm going to refer to this polynomial time algorithm as a polynomial time verifier or verification algorithm. That can verify it is a yes instance. So remember, I must stress that your job is not to just like, I give you the instance, your job is just to solve it or something. No. The game here, so go back to the game plan. The game plan here is very simple. They give you some short proof. If I call this, say, for example, y. So if I give you a short proof, and I give you, and I'm going to add one little detail here, from instance x. So you're given x and you're given y. If x is a yes instance, your job is just to check if y, in fact, is going to lead you, if x is a yes instance, that you can verify from this proof that indeed it is a yes instance. So your job is just to check it, not to construct a solution. So this is going to be a little strange to hear. Is that strange? Sounds strange to anybody? Don't be shy. It sounds kind of weird at first. It's a kind of a weird intuition at first. But just follow with me carefully. So here's an idea. So just to give you an intuition for this. Okay, has anybody ever, this is just to give you a fun analogy. So imagine if you had, say, a dog, or I'm not sure if anybody has ever heard of the show called Lassie, but to give you the idea, this is kind of like a super dog. It's this dog that's capable of rescuing and helping people all over the place, named Lassie. And Lassie will help people with all sorts of things, like a little Billy or a little Sally's in the well. Lassie will tell you where little Billy and little Sally is. So imagine I gave you this scenario where like Billy or Sally are in this well. And Lassie comes up to you and goes, "Woof, woof, 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 woof." And he's like, "Oh, what is it, Lassie?" and Lassie will lead you to the well. Now, imagine if Lassie was not there and I knew that Sally or Billy was missing. Now, if I didn't have Lassie, now I'm assuming that Billy and Sally are actually out there, would you tell me, if I didn't have Lassie to help guide me over to Billy and Sally, because Lassie's just really that incredible, would you tell me that probably if I had no information, it'd probably be a lot harder to find Billy or Sally? Do you get the idea? So imagine if I give you the process of, say, for example, Lassie has to route through a graph finding a Hamiltonian cycle. So what Lassie could do is follow you through where the cycle might be, if it's a yes answer. And all you have to do is follow Lassie around through the cycle. And you could just check that Lassie indeed found a Hamiltonian cycle. This is in contrast to me knowing nothing about where a potential cycle is, and I have to find it myself. So one intuition for this is the construction of a solution versus me checking a solution. Does everybody see the difference between these two things? So if I gave you some cycle, say like Lassie's like, it gives me a cycle in one of my Hamiltonian cycle instances. Can somebody tell me how I would check if I have a Hamiltonian cycle, if it actually is there? Assuming I'm given one of these proofs, just some cycle. So think about it just like if you're checking. So you don't even need to go to backtracking. Just think of the most simplest thing. Oh, backtracing. So yeah, so what would you do if you're thinking about backtracing through this? So if somebody gives you a cycle, so imagine that is the proof that somebody gives you. So if somebody gives you a cycle, all you have to do is check that that cycle is a Hamiltonian cycle. So what would you do? There's really just one really, well, there's really kind of a couple things you have to check, right? So first, that the Hamiltonian, the cycle that I'm given contains all the vertices, right? It has to contain all the vertices in the graph G. But it also cannot repeat a single vertex twice, right? So all you do is you follow those edges. You just follow the edges in the cycle. So you just follow Lassie, just going through there and find Billy and Sally. And it ends up Billy and Sally is actually in the backyard. So do you see how I can do that in polynomial time? In fact, I could do that quite quickly. It's actually, I could do that in quadratic time. Quadratic in the number of vertices. Does everybody get the general idea? So my job is given some proof, assuming I'm given a yes answer so I give it an instance that has a yes answer. My job is just to verify whether that proof is indeed going to lead me to a yes answer, or it should spit out saying, hey, look, this is not a Hamiltonian cycle. That proof is a bunch of nonsense. So I'm just checking the proof. That's my job. Just to be very clear, because it's a very common mistake that some people make, is that my job with this polynomial time verification algorithm is not to say that X has a no instance. Job is not to do that. It's just to check if Y is it's not a Hamiltonian cycle. So I just want to give you some examples of what these proofs might look like. So as long as there exists one of these short proofs that's a polynomial length in the input size, which most of the time the proof is very obvious when you run into it. It's usually what a solution would look like, because normally your solution is not going to be exponentially large. It's usually polynomial in the size of the input. Usually. So what is a proof? So here's just so it can look like what a solution to a yes instance should be. So just to give you some concrete examples, so if I have the decision version of minimum spanning tree, so if I give you this problem, you could just simply give me a spanning tree. You can just simply give me a spanning tree. And what would the verification algorithm look like if somebody just gives you a spanning tree and they tell you, hey, look, tell me, is this spanning tree, like first, is this a spanning tree? And two, what is the other criteria that I need to check? So in this decision version, I'm given a graph, and also I'm given that integer k. So what would the verification algorithm look like here? Could somebody just give me a high-level view of what that might look like? So remember, just think of Lassie just going, and try, and Lassie's job is just to lead you the way to know that, hey, look, is it actually a yes instance? Or did Lassie lead you the wrong way? So I'll give you an idea. you can check that it is a spanning tree. So you just check if it has all the vertices of the graph. And check its total cost is at most k. Sorry, no question mark, no question mark. It's most k. And if both of these are answered yes, then you know it's indeed a yes answer. If any of these two fail, then you know it's that you better not believe that proof, okay? Means Lassie duped you. So if you wanted a little bit of an intuition behind this, you can imagine if I gave you all possible pathways to solve for a solution. Think of it almost like when we did brute force. Remember I had that big tree where I forked out all those decisions, and each branch of my tree corresponded to a decision that I made. Now imagine if there was a pathway that led me down to some leaf that was an answer that's a yes answer. So imagine if I did this. You can imagine that what I'm describing here, one of these proofs would actually correspond to one of the pathways along one of these brute force trees, which has a natural correspondence to something I'm going to mention in a moment. But a no answer would simply be, you would have to check it against all the possible pathways, which is very difficult. So all you have to do when we have this verification algorithm is just check one of these pathways. That's really all that's really happening. So that's kind of the behind the scenes of what I mean. So if somebody just gives you one of these certificates or proofs, your job is just to check it against the instance and see, yeah, that's definitely going to be yes. So we have two parts. Identifying one of these proofs, see if it exists. So we get to choose what the proof looks like. And then all you have to do is give a polynomial time algorithm that verifies that proof to say if it's yes or no given instance x. So just give you another idea. So if I give you Hamiltonian cycle, you can just give me a cycle. And this is exactly what I mentioned earlier. So I mentioned what you would do for the verification algorithm here. And with TSP decision, you could give me simply a TSP TOR. Now, for this one, can somebody tell me what the verification algorithm would look like? It's quite similar to the one for the Hamiltonian cycle that I mentioned earlier. Can somebody tell me what it should do? So if I give you some TSP TOR, what's your job to do? What's the verification algorithm got to do? It's just going to tell me, is that a TSP TOR that's going to be what? And what is a TSP TOR in the first place? So could somebody tell me what that should look like? So just think about it in terms of checking. Like, so if I give you a TSP TOR, your job is to tell me if its total length is at most k, and in fact it is a TSP TOR, right? So you could just simply say it's a cycle again. So a cycle suffices actually as a proof as well here. Just the way I formulated our TSP instances, they're always going to be a TSP TOR if I give you some cycle that goes through all of the graph. So either of these could be also technically proofs in this case, just you would have to check a couple of things here. So these are examples of what one of these proofs could look like, and all we care about is that there exists one of these proofs that's of polynomial length in the input size, and that there's some polynomial time algorithm I can use to check it. So everybody got the general idea of this. So just the high level, like if you're really not entirely sure, that's okay. This is a pretty tricky concept. But if you got it, wonderful. So that brings me to talking about another complexity class. So I'm going to define this as NP. So I'll tell you that a decision problem pi is in NP if there is a polynomial time verifier or verification algorithm for it. Another way to cast this is that and this is where the name of this comes from. Another way you can cast this definition is that NP is the class of decision problems. Sorry, the class of decision problems that can be solved in non-deterministic polynomial time. So that says non-deterministic. Now there's a very specific meaning that non-deterministic has, and it actually matches quite closely to the, hey, no worries, no, thank you. The, now have yourself and best of luck. So when you hear this, you shouldn't think random. Don't think like, oh yeah, non-deterministic meaning like that. It's a different notion of this. No, best of luck. So when I do this, if you're curious about the details of what this non-deterministic means, it actually corresponds quite closely to the tree I was talking about earlier on. If you're curious more about this, take CS 411. We talk exactly about what this means. So there's a natural correspondence between these verifiers and the existence of these non-deterministic polynomial time algorithms. Essentially, they tantamount to guesses and checking if the guess is in fact a yes or not, which is what I effectively told you here, is that imagine somebody gives you some guess and your job is to tell me, yeah, that is going to be, for my yes instances, it'll definitely be a yes. So I've defined two classes for you. I've defined P and NP, but I want to kind of put these two things together for you. And this actually boils down to something that you may have heard of. This is a very infamous problem in computer science. It's often considered the most important open problem of all computer science problems. Is that we really don't, I want to point out one interesting connection, because I talked about P and NP. So, believe it or not, we know that actually P is a subset of NP. We actually know this. This is simply because whenever I give you a decision problem, and say it's in P, believe it or not, all you have to do to design your polynomial time verifier, because I already have a polynomial time algorithm that decides yes and no answers for my decision problem if it's in P. I don't have to do anything with that proof, right? I could just simply solve the instance and I could tell you yes or no, right? I could just straight up, in most technical senses, you would ignore the proof and you would just solve it directly. Another notion is that every deterministic algorithm is a special kind of non-deterministic algorithm. But I don't want to get to those technical details here. But we don't, so this is indeed the case. So if somebody asked you if that's the case, the answer is yes. However, if you're trying to prove that these two sets are equal to one another, we don't know the answer to the latter. And there are serious implications if the answer is yes. If the answer is yes, there's serious implications to this. So if you ever wonder what the P versus NP problem is, it's simply that we're asking if P is equal to NP. I don't want to bias you in any one direction or another, but very often, if you talk to a lot of theoreticians, they usually tell you that they're not equal, but they have evidence for these sorts of things. If you talk to most of them, they tend to say that they're not equal. Each of them sort of has their own intuition for it, but this is an open problem. We don't have a proof one way or the other. We have evidence, and we could have discussions about that kind of evidence. But I want to kind of give us some machinery to talk about this. It brings me to talking about NP-completeness. So the first thing I should point out to you is if I look at the complexity class NP, there's actually hardest problems in there. So there are hardest problems in NP. To define this, I'm going to define something we call NP hard. And it's based entirely around a polynomial time reduction. So NP hard, so I'll tell you a problem pi, and I must stress that I'm using the word problem here explicitly because some problems don't necessarily have to be decision problems to be NP hard. This is just because of the nature of what I'm going to say in a moment. So for example, you can have an optimization problem that's NP hard. That's very often how we talk about problems that are what we're going to define in a moment when I want to talk about their optimization versions, because usually they're at least as hard as these. So problem pi is NP hard if for every pi prime in NP, pi prime has a polynomial time reduction to pi. So it means I could take any one decision problem that's sitting in NP, and I can give you a polynomial time reduction that gets me over to my problem pi. This sounds really strange, right? So I've told you that there's some recipe that in polynomial time that I could turn, at least if I presume that these exist, I could take any problem in NP and turn it into my problem pi. Why call it problem pi? That's its name. I just called it that. You could call it apples if you wanted to. Usually theoreticians like me like using symbols like these because they're very common. Pi starts with the letter P. It's very natural. Now I have to define what is called NP-complete. So I haven't really told you that there are problems that are these yet. But a decision problem, so now notice the distinction here. Decision problem pi. But yeah, the easy way to remember this is that pi means, it starts with this letter P, right? Decision problem pi is NP-complete if two things. Pi is in NP, so that's the first criteria. The other criteria is that pi is NP hard. Well, it's capital pi. It's just a symbol. So anyways, so we have NP-complete. So keep in mind, it has these two criteria. Now, there's a very strange thing that you should know about this, is that there actually do exist NP-complete problems. So this one was first discovered in the 1970s. It's called the satisfiability problem. It's abbreviated as SAT. Is NP-complete. If you're wondering what this is, you give me some arbitrary Boolean formula that consists of ands or ors or nots. So I imagine I can have my binary variables. So either they have true or false values. And imagine I give you an arbitrary one of these formulas that consists of ands, ors, or nots. It has to be a valid formula, meaning that it can't have weird semantic issues with it. And it can have parentheses the group terms. So if I give you one of these arbitrarily, that is actually, and if I want to know some assignment of the variables such that it yields a overall true value for that expression, you could think of this like if I give you a really complicated if statement and I ask you, is there some way I can assign the variables in my if statement's conditions such that it yields true? This decision problem is what we call satisfiability. It's a rather interesting problem. But the best known algorithms we have for this one take exponential time. In practice, there are solvers that do quite well, but from an exact standpoint, we're still dealing with exponential time here. So I want to stress that there's an interesting thing that happens as a result of this. Now remember, I gave you in this definition two things, that it's an NP and it's NP hard. And this is entirely based on polynomial time reduction, so I have two criteria. Here's the thing you could do once you have an NP-complete problem, and entirely based around what I showed you the other day. Let's watch this. So this is kind of like the killer app of polynomial time reductions. So if somebody asks you, hey Dan, like if I have all these problems, and the hardest ones we don't really have, for our best of our knowledge, remember, I don't know, but to the best of our knowledge, we do not have polynomial time algorithms for these hardest problems in NP. I would like to be able to convince somebody that my problem also belongs to those NP-complete ones. And that comes back to the polynomial time reduction. So here's an alternate definition of NP-complete. So if pi is NP-complete, and pi prime is in NP, so pi prime is a different problem. That's the one you're typically interested in. And there's a polynomial time reduction from pi to pi prime. Then pi prime is also NP-complete. I must stress that if you do not have this other condition, you can actually see that pi prime is actually NP-hard. It's very often how NP-hard proofs go down. So there's many problems that sit in different domains that actually are proven using this way. So just as a quick example of a list of them, so for example, many problems are actually shown to be NP-complete, such as packing problems, such as, for example, our 0-1 knapsack problem. Its decision version is NP-complete. Its optimization version is NP-hard. What you do is you use a series of these reductions starting from SAT, and you work your way up using other problems you establish using this, what I've just described here. So you work your way up using reductions. And because each one takes polynomial time, the overall running time of whatever you do takes polynomial time. That's the game. So, for example, I could give you packing problems. I could talk about coloring problems. I'm just wrapping things up here. I have one final theorem to give you. So coloring problems. So, for example, if I give you a graph, and I would like to know if there's a way I can assign colors to the vertices. So for example, if I wanted to make this one, say, red, and I want to make this one, say, blue, is there some way I can assign the colors such that I use at most 3 colors? So for example, if I have a red, blue, and a green, is there any way I can color the remainder of this graph? And the answer in this case is unfortunately no. You need more colors. A problem called 3 coloring in this domain is NP-complete. But I must warn you is that there also are special cases of these kinds of problems that actually do belong to P. For example, 2 coloring is actually in P. It's because it's exactly the same as testing if a graph is what we call bipartite. So this is actually based on bipartite testing. So if you want to test if a graph is bipartite, this is actually equivalent to this. We didn't talk about that, but I also want to mention that many scheduling problems, many scheduling problems are, in fact, NP-complete. For example, multiprocessor scheduling. Is NP-complete. I have some more specific examples in the notes for these, but I just wanted to give you some flavor for there's many, many fundamental problems that affect many domains in industry, in practice, everywhere you're going to find these. I must stress, you'll find them all over the place. There's thousands upon thousands of these that people have in the literature. But here's the theorem I want to present, and this is actually the very last thing I'm presenting to you this course. Here's the theorem. So if some NP-complete problem is in P, then P is equal to NP. So it means that if you can change the world by just simply finding for any problem that you could find that's NP-complete, and if you could determine that there exists a polynomial time algorithm for it, then you could show that P is equal to NP. So this is the direct consequence of reductions. So that being said, I apologize for going a little longer here, but I really need to get to this theorem here. But this has serious implications. It resolves the P versus NP question. And there's many of these problems, and you will run into them. So that being said, I want to say thank you very much. It was a pleasure hanging on out with everybody. And also I want to be very thankful because it's always a wonderful opportunity to be out in front of everybody and and it's an honor to be able to teach students. I must stress that it's been a wonderful term. I want to say thank you very much for being such wonderful students this term. It's always a pleasure to be in front of students doing these things. So that being said, I want to wish you the best with the final exam. And thank you very much, and have yourself a beautiful day. I'll see everybody later, okay? It was a great term, everybody.